We have second presentation on our Python Summit. This time, I'm talking like Maria from Intel would talk about fundamental decision making. Like I'm sure that everyone who ever dealt with software engineering had this discussion at the very beginning. Okay, what we should choose, what framework, what technology, like not a programming language because Python is obvious, right? It is in this field at least. But we sit down with our folks and discuss, okay, which one we're going to use, which one will be better for our current use case and for our future use cases. And actually, this is a fundamental question because the decision you make at this point will influence whatever you do in the next sprints, in the next development phases. And like everyone was also in this situation that they had to slightly change the technology because the product or the software went a bit of over what is supposed to be at the very beginning. So Maria, very important topic on choosing the deep learning frameworks. The stage is yours.
Thank you. Thank you so much. So hi, everyone. My name is Maria. And as we just said, I'm here to help you to make sense of all the different ways that Python shines in the world of deep learning today. But before we dive in, let me just share a quick fun fact about myself. Python was actually the first language that I learned how to code, and it was just what made me fall in love with coding. And fast forward to today, I have over a decade of experience working in leading tech companies. And for the past 5 years, my focus has been entirely on AI deep learning, and more specifically, deep learning runtime and deep learning communication at large scale. Currently, I lead the runtime team at Habana Labs, which is at an Intel company. And this is the company that was the creator of the Gaudi accelerator for deep learning training and inference. And my team basically handles all the core runtime aspects of deep learning, things like synchronization, hardware resource management, graph execution, and many more fascinating challenges. So let's start. What's on the agenda today? First, we will understand what a framework actually is, and then go over some core terms and principles that every deep learning framework is built on, such as graph versus eager and static versus dynamic graphs. After the fundamentals, we'll move to the evolution of frameworks. Next, we'll highlight the strengths of the popular ones, and we will explore large-scale training, which is becoming the defining factor of modern AI. And we talk about why scale matters so much, and what changes when you go from one accelerator to thousands, and how different frameworks handle this distributed compute scene. We will discuss deployment and production, because building a great model is one thing, but shipping it reliably is another story entirely. And lastly, we will look at the ecosystem and tooling these frameworks use in real-world scenarios. I think that by the end of this session, you will have a clear, practical map of the deep learning frameworks landscape in 2025 and when to choose which framework depending on your goals. So, as I mentioned, before we dive into the deep learning framework showdown, let's start with a simple question. What exactly are frameworks and why do we need them? So imagine trying to train a neural network completely from scratch. You'd have to manually code every single matrix multiplication, calculate every gradient, update every weight, and somehow make it all run efficiently on a chip or even across multiple machines. This is not just tedious, it's impossible at scale. So deep learning frameworks exist to hide specifically this complexity and make it possible for us to focus on the ideas and not the math. They handle all the heavy lifting, such as automatic differentiation, so we don't have to compute gradients by hand. They handle the hardware acceleration. They run our code seamlessly on CPUs, GPUs, TPUs, and custom accelerators like Gaudi. They handle model management, saving, loading, training, and deploying models with a few lines of code. So in other words, frameworks turn deep learning from a research experiment to an engineering discipline. They let us go from theory to production, and they do that fast. Let's take a moment to look at this illustration. On the left, we can see how chaotic and complex things used to be. Every line of code had to handle the math, the gradients, and the details manually. On the right, we see a completely different story. Clean, simple, and elegant. This contrast beautifully captures the true power of deep learning frameworks. They transform something once messy and technical into something intuitive and creative. Now, since we all come from different backgrounds, I'd like to take a moment to explain some crucial concepts that will make the rest of this talk much easier to follow. The first concept would be our work mode, and in other words, graph versus eager mode. This is to do with what actually happens to our training operations during runtime. It might sound technical, but it's actually quite intuitive once you see the difference. In graph mode, you don't actually run your operations immediately. Instead, you first define a computation graph. This is like a flowchart describing how data should move through your model. Then in a separate step, you execute that graph with real data. This approach might sound a bit clunky, but it has a huge advantage. Because the entire graph is known in advance, the framework can optimize it before execution. Things like merging operations, reordering for efficiency, and distributing work across hardware engines. That's why graph mode is highly performant and still preferred for large-scale production deployments. The downside is that it's harder to debug, because when you write your code, nothing actually runs until you execute the graph itself. So if you made a mistake, you often don't see it until much, much later. In eager mode, everything runs immediately, line by line, just like normal Python code. It's much more intuitive. You can print tensors, inspect values, and debug easily. No separate graph compilation step. This makes it ideal for researchers and prototyping, when you want fast feedback and interactivity. The trade-off is that eager mode is way slower, because the framework cannot optimize the entire computation graph ahead of time. Rather, it executes operations one by one. So you can think of it like this. Graph mode is like compiling a recipe before cooking, efficient and repeatable once you know exactly what you're doing. On the other hand, eager mode is like cooking step by step, tasting and adjusting as you go. Now let's discuss graphs specifically and understand the difference between dynamic and static graphs. Or in other words, whether the graph can change during runtime. Deep learning frameworks differ not just in syntax or APIs, but in how they execute your model. And this choice fundamentally affects flexibility, debugging, and performance. So a static graph means that the entire computation graph is constructed once before execution. Because the graph is fixed, the compiler can aggressively optimize it. It can fuse operations, eliminate dead code, reallocate memory, and map the graph perfectly onto the hardware. This is why static graphs shine in production, where performance is crucial. On the other side, we have dynamic graphs, where the graph is created on the fly every time you run forward. This provides amazing flexibility. The network can change shape during execution using regular Python control flow and be debugged line by line. Dynamic graphs are intuitive, fast to prototype, and perfect for research, where you're constantly experimenting and iterating. The trade-off? Dynamic graphs are harder to optimize ahead of time. You get flexibility, but you have to give up performance. Now, let's look at how Python deep learning frameworks have evolved over time. It all began with Theano, one of the earliest deep learning frameworks. Theano introduced the idea of defining computations as mathematical graphs, and that concept became the foundation for everything that followed. It paved the way for modern deep learning as we know it today. Then came TensorFlow, which took deep learning from research to large-scale production. TensorFlow revolutionized the space by focusing on scalability, distributed training, and robust integration across hardwares, from CPUs, GPUs, and TPUs. It became the go-to choice for companies that needed reliability and performance. A few years later, PyTorch arrived and completely changed the landscape again. PyTorch was built with flexibility and simplicity in mind. It gave researchers a way to write models that felt like normal Python code. It quickly became the favorite in the research community because it was so intuitive and dynamic. Next, we have JAX, which represents a more recent evolution. JAX combines functional programming with automatic differentiation and XLA compilation, allowing incredibly fast, optimized code execution. It's very popular among advanced researchers and teams pushing the boundaries of model performance and scale. Now, let's focus on the stars of this evolution. In other words, TensorFlow, PyTorch, and JAX. They all speak the same language, but each with its own unique accent, personality, and philosophy. Firstly, TensorFlow and Keras, the framework duo that really define deep learning at scale. TensorFlow was created by Google Brain in 2015, and it became the standard for building production-grade AI systems. It's powerful, scalable, and built to handle everything from research to deployment across massive infrastructures. On top of it sits Keras, which acts as the friendly face of TensorFlow, a high-level API that lets you build the trained models just with a few lines of code. Together, they form the perfect balance. TensorFlow handles all the heavy lifting, performance, optimization, and distributed execution, while Keras makes the workflow fast, intuitive, and human-friendly. TensorFlow and Keras really shine when it comes to production and scalability. They're the go-to choice for companies that need to take a model all the way from research to real-world deployment. They're also fantastic for cross-platform machine learning. The same model can run on mobile devices, in the browser, or in massive cloud clusters using GPUs or TPUs. Another major strength is the stable and integrated pipelines. TensorFlow offers a complete ecosystem. TensorBoard for visualization, TensorFlow serving for deployment, and TFX for managing data and training pipelines. So overall, TensorFlow and Keras are best for when you need reliability, performance, and long-term maintainability, when your goal isn't just to experiment, but rather to scale. Now let's discuss PyTorch, the framework that truly changed how people think about deep learning. It was developed by Meta's AI research team in 2016. PyTorch introduced a completely new level of flexibility and interactivity. Its biggest innovation was the dynamic computation graph, meant that operations run immediately, line by line, just like regular Python code. This made it intuitive, transparent, and easy to debug, which is why it quickly became the favorite among researchers and other companies. The PyTorch AI framework is also widely considered the best choice and de facto standard for working in eager execution mode. So basically, PyTorch was designed around immediate execution from day one, which made it the most intuitive framework. Even though it now supports compilation, its core philosophy is still eager first. PyTorch, as mentioned, is best for research, experimentation, and innovation. It is the framework of choice in academia and cutting AI labs because it allows researchers to iterate quickly and try new ideas without friction. It's also great for rapid prototyping. When you want to test a concept, tweak a model, or explore a new architecture, PyTorch gives you the instant feedback. And in recent years, PyTorch has grown beyond research. With tools like TorchScript, it now bridges the gap from research to production. So in short, if you want to move fast, experiment freely, and stay close to the Python experiment, PyTorch is your best friend. And finally, we have JAX, the framework that brings together mathematical elegance and raw performance. JAX was developed by Google Research, and it feels a lot like NumPy, but supercharged. It combines familiar Python syntax with automatic differentiation and XLA compilation, which allows it to run incredibly fast on GPUs or TPUs. What makes JAX special is that it was built for performance and scalability from the ground up. It's not just about training neural networks, it's about building the kind of custom experimental high-performance models that push the boundaries of large scale. So JAX really shines in advanced research and high-performance computing. It's the tool of choice for teams working at the cutting edge, like DeepMind and Anthropic, where speed, parallelism, and precision matter most. It's also perfect for multi-device and multi-node training. JAX makes it surprisingly easy to scale computations across clusters or TPUs. In short, JAX is for those who need maximum control and efficiency, and who aren't afraid to trade a bit of simplicity for raw computational power. If TensorFlow is the production power horse and PyTorch is the researcher's playground, then JAX is the performance lab. Now let us dive into one of the most practical aspects of these frameworks, their ecosystems and tooling. Because in real-world deep learning, the framework itself is only part of the story. What really matters is the ecosystem that surrounds it. Now let's start with PyTorch. PyTorch has built a rich and vibrant ecosystem that's loved by developers. You've got tools like PyTorch Lightning for structured training, TorchX for deployment, and integrations with Hugging Face, which powers many of today's cutting-edge NLP models. These strong ecosystems give PyTorch a real advantage in productivity and flexibility, especially for research and rapid experimentation. Moving to TensorFlow, this one is all about scale and reliability. TensorFlow's ecosystem is extremely comprehensive. TFX provides full production pipelines. TensorBoard lets you visualize metrics and performance. And TF Serving handles deployment at scale. Together, these make TensorFlow a solid choice for enterprise-grade end-to-end machine learning solutions. And then there's JAX, the new, more research-oriented framework. JAX leans into functional programming, so its ecosystem is evolving fast. You'll often see libraries like Flex and Haiku for building neural networks and Optax for optimization. These libraries make JAX incredibly powerful for high-performance research, especially when running on TPUs or large clusters. Finally, a quick note on ecosystem maturity. This plays a huge role. More mature ecosystems, like TensorFlow's, offer stability and integration, where newer ones like JAX prioritize innovation and speed. So when teams choose a framework, they're not just picking a coding style, they're choosing an entire ecosystem that determines how easily they can train, deploy, and scale their models. Now, as promised, we must spotlight the aspect of large scale in today's deep learning. Over the last years, we've learned something remarkable. When you increase model size, data quantity, and compute in the right proportion, performance improves in a highly predictable way. Large models simply learn richer and more abstract representations. They reason better, generalize better, handle edge cases better, and they're more robust when deployed. And this is not just quality. Scale accelerates iteration speed. So if your team can train in days instead of months, you unlock an entirely different rate of innovation. You can run more experiments, test more hypotheses, and push research forward dramatically faster. Finally, there's the competitive reality. The frontier of AI is defined by organizations training at planetary scale, multi-billion parameter models on thousands of accelerators. If you're not scaling your training infrastructure, you fall behind not just in performance, but in the pace at which you can ship new capabilities. So in short, scale isn't a luxury anymore. It's the foundation of modern AI progress. And for such scale, distributed training has become essential. With that in mind, let's explore how the three major frameworks, PyTorch, TensorFlow, and JAX, approach distributed training. Starting with PyTorch. PyTorch uses Torch Distributed and FSDP, fully shared data parallel, to enable multi-node and multi-GPU training with minimal overhead. It's designed for flexibility, supporting both data and model parallelism. PyTorch also integrates with DeepSpeed, which is especially powerful for large models like LLMs, helping to reduce memory usage and improve scalability. TensorFlow's TF distribute strategy offers a variety of options for scaling across devices, from single machine setup with multiple GPUs to massive multi-node clusters. And when paired with Horovod, TensorFlow makes it easier for teams to train large models efficiently while keeping their code base portable across environments. And then there's JAX, which takes a more composable approach. It provides primitives like PMAP, PGIT, and XMAP that allow developers to distribute computation seamlessly across multiple devices. This approach gives researchers incredible control and performance tuning capabilities, ideal for high-performance workloads. Now that we've seen how models train and scale, let's talk about the final step, deployment and production. This is where the machine learning stops being a research experiment and starts delivering real-world value. PyTorch provides a dedicated deployment tool called TorchServe. It allows teams to serve PyTorch models at scale, whether on-premise or in the cloud, while maintaining flexibility and high performance. TorchServe supports features like multi-node serving, version management, and auto-scaling, making it a great fit for enterprise environments that need stability and control. Moving to TensorFlow, we have TF serving, which is one of the most mature deployment frameworks out there. It's built for speed, stability, and versioning. TF serving handles large production workloads efficiently, making it easy to roll out model versions and A/B test models with minimal overhead. That's why many large-scale companies still rely on TensorFlow in production, even if they prototype using PyTorch. With JAX, things work a bit differently. Since JAX was designed primarily for research, it doesn't have a single official serving solution, but it offers great flexibility. Custom deployment setups can integrate with high-performance hardware like TPUs or accelerators, which makes JAX ideal for specialized environments, particularly in research labs and companies with custom infrastructure. So the landscape of Python deep learning frameworks is evolving rapidly. As we look towards the future, it's essential to understand the unique strengths of each framework. PyTorch is ideal for researchers aiming for rapid experimentation, while TensorFlow Keras is preferred for production-level solutions due to its stability and scalability. JAX offers cutting-edge capabilities for high-performance training, particularly in research training. In 2025, the emphasis is on hybrid stacks and cloud-native ML, requiring developers to choose frameworks based on specific use cases rather than adhering to a one-size-fits-all solution. With accelerator awareness becoming critical, understanding how each framework interacts with diverse hardware will influence performance outcomes. Ultimately, the right choice hinges on your unique needs and goals, making it imperative to stay informed on this framework's development. So thank you, everyone. I think we finished a bit ahead of time. So if someone has any questions.
Yes, please remember that we have questions from the chat. So you can ask questions over there to our speakers. We have a QR code that we would like you to use to give your feedback, basically. Maria, I have a very basic question for you.
Yeah, because, of course, go ahead.
Because you introduced us to how to the decision-making process on how to choose the perfect framework for our tool. So first of all, have you learned that a hard way, or you did the research before?
So basically, I myself am positioned very low in the software stack. Mm-hmm. I never work with frameworks. It's just something I was interested about. So I learned about that. But my team is a core component. So we write our code above the driver, so close to hardware. And the framework is like our user, to say. Okay. So yeah, and basically because my company works with both PyTorch and TensorFlow, So I had the opportunity to hear a lot about the outcomes of each framework over the years. So I decided to experiment a bit myself and to learn deeper, because I always was thinking, why do we have to use all of them? Why can't we just use one? And that just led me to read about that and learn. And I wanted to share that with other people.
Okay, great. What about the situation where we choose, like we assume we're gonna choose framework A, but then we realize like when this reflection point should come? Have you
Yeah,
ever
that's
thought
a
about
big
that?
one. Yeah, that's a big one. I think fortunately, no matter what you go with today, as I mentioned, all of them have a lot of capabilities. So it's not like you're going to have a major crisis. You might have a workflow that is that's working less good with what you aim for, but you will be able to do everything, because essentially, even if you use PyTorch or even if you use TensorFlow, for instance, you can eventually deliver the product. It's just it's just the question of how nicely it's going to run for you and how good it's going to fit your needs. But either way, no matter what you go with, you're going to be able to deploy. And I think that, yes, this is the moment, like, I think that the realization should come very early, because when planning a product, you need to think ahead. You need to understand, do you need scale? Do you need fast iterations? What is the environment you're going to use? As I said, hardware understanding is very important, because if you're going to use TPUs, you better use Google products. If you're going to use custom accelerators or GPUs, you're more free to play with other frameworks. But essentially, the faster you make the decision, and you see your whole roadmap and your architecture ahead, the best fit you're going to get. Of course, not always it's possible, but essentially that is what we should aim for, I think.
Okay. All right. So generally speaking, it's better to analyze at the very beginning and think a bit of ahead and talk to your financial person regarding technology and the cloud you're going to use. Because at the end, all of this runs on a hardware itself.
Exactly. You need to remember that. Yes.
Yeah. So we can be software engineers, but the code is run somewhere.
You need to be hardware aware, at least.
Yes.
It's very important. Yes.
Okay. Thank you for your comments, for answering these questions, and for the whole presentation. I hope you enjoy the rest of the day in terms of our conference, and there's also VOD. So I hope you'll find something for yourself as well.
Thank you, of course.
Yeah, and when you're in Poland, definitely let us know. As our Python communities, we're organizing a bunch of different events, and we'll be more than happy to host you here.
I would be delighted. Thank you. Thank you
so much.
Thank you.
And have a good day.